Hello guys, welcome back. Today I will talk about something uh, that is quite important in classical physics and quantum mechanics as well. It's called coherence. Um, coherence, coherence, and it's basically um, I want to talk about this because a friend of mine asked me I think a very interesting question, and the question was like, why uh, does laser light travels farther away rather than just a bulb incandescent light travels further away than bulb lights? Question mark. Okay, so why? So laser light and bulb lights, and so it's not super easy to give an idea of why this is the case, and also we need it involves a lot of equation, Maxwell's equation and Laser's equation, which I'm not going to give in any detail whatsoever, but I will give an idea of what I understood and why this is the case, and at the end I will give a short a representation, visual representation of this idea. So first of all, let's discuss a little bit of what could mean coherence. Coherence, in the way I use it, is when you have two waves. Suppose we know sinusoidal and cosinusoid, right? We saw them in other videos. We studied them in quite details, and this can be either a sinus or cosinus depending where you put the initial condition, right? In this way would be a cosinus, while in this way would be a sinus. Okay, depending where the zero is, you get a sinus or a cosinus. It's just a difference in the phase, in the initial phase. In fact, I think that sinus of t plus a phase pi over 2 should be cosinus of t. There might be some plus or minus that I never quite get right, depending on which is the sinus here. But anyway, roughly, let's say it's a shift in the phase, and it's exactly this phase here that is we call it phi usually. That is what coherence is all about. Okay, let's see if I can give you an idea of this, and then we will answer the question of laser light and bulb light. Okay, so first of all, I will give you a picture of what a incandescent, even an LED. We can talk about LED and laser. Let's say LED, light emitting diode, and laser. So think about an LED as an object, like a source. Usually it's made out of a semiconductor. The physics is very exciting and interesting. I'm not going into any detail of that, but we know that it emits wiggles of light in many directions. Okay, and depending on the color of the LED, it can be blue, it can be green, it can be of a particular dye, particular color. Let's say in this case, it's orange. I don't think it exists, so let's pick a green LED, which emits squiggle of light, photons basically, and in many directions. And each of these, it can be thought as a short sine t plus some phase. plus some phase that depends on t as well, depending on the emission time of the and this is the amplitude I. So for each of these we have amplitude I, which we know it's a complex number. It could be a complex number. In this case, it is a complex number with just the imaginary part equal to 0. We know that e to the I phi, e to the I, let's say a, is equal to sinus a plus I cosinus a, or vice versa. But anyway, this is a cosinus and this is a sinus. Make it clear. This is a cosinus and this is a sinus. So we can this is a subset of this, okay? Or the cosinus or the sinus, you pick the correct phase. It doesn't matter. But we know that each of this squiggle of light, this photon, let's say, can be many photons at once that behave like a sinusoid. They, if you plot them in time in one dimension, thinking that we just think about the amplitude in any given direction. So this is the amplitude intensity, for example, which we know that is intensity is the amplitude I modulus square. We know modulus square because we already talked about this in other videos. To take from the amplitude to the probability, you get the amplitude square. But also in classical physics, the intensity is the amplitude square of the electric field. So this is true in both cases. But we know that each of these intensity is a sinus square, which we'll draw it like this. Okay, it's an oscillation for some time. The point is that the initial phase is different. So it could be this, the second one it could be another, the third one would be yet another one, the fourth one would be, I don't know, starting from here, and so on and so forth. So each of these components we will be one of these squiggle lines that I draw here. And essentially the fact that the initial phase is not the same, it doesn't give much. It basically gives a summation of random values in this direction in the intensity, which will be some value, let's say mean value here, which we don't know what it is. It will vary with time, and it will be basically the same in any direction. So in any of these direction, you will have many contributions of this kind. So in this sense, the summation, and you can see that this depends on the phase only. You can also add an amplitude which varies and will be adding some structure on the mean. So what I'm drawing in orange is the average, which is a sum of all the amplitudes divided by the number of the amplitudes, okay? 1 to n. It's literally the average of this value, and actually the value, the modulus square of it. And this is the average intensity, okay? Which we'll call it I bar, which is a symbol that says average intensity. So, and the fact that there is no preferential direction is essentially because this randomization of the phases is also true for the space, the angular distribution. So the amplitude of each of each of these as photons, let's say, or waves, depending on the phase, is also random, okay? And therefore there is no preferential direction. Okay, so we understand that this, and we call this not coherent, because the phases are random and do not adapt constructively or destructively for whatever reason. Let's see what it means to be coherence instead. For example, if you have a laser, which is an interesting acronym, light amplification, stimulated emitting, emission, radiation, something like that. I never remember quite what's the acronym of it. I will put it in the description anyway. But those are two acronyms: light emitting diode and light emission by light amplification by stimulated emission radiation. Something like that. Sorry, but so this is not coherent. Not as much as we want, and definitely the bulb light, or the bulb, which is just a piece of metal which is heated up, will be not coherent as well, because the emission of photons is random and depends on the temperature of the bulb incandescent light, and the same apply to the phases. Okay, the only difference is that the light emitting diode can be tuned to a precise color, while the bulb will have many colors inside, depending on the temperature, and therefore you can have white light out of a single incandescent piece of tungsten, for example, or other metals. Okay, but these are not coherent because the phase is random. The phase is random. So how do you make it coherent then? Just by locking. If you lock the phase, locking the phases, meaning that all those phi of t of I will be equal to the same value phi, and that means that all the emitting light they can have different amplitude possibly, but the initial condition is exactly the same. Okay, maybe a little difference, but if you want, you can draw them like this, and they will be all perfectly in phase, because sinus of t plus phi doesn't change in time, t changes in time, but the other one change. Ty plus phi bar, phi is the same, and the same as sinusoidal t I plus phi bar. The amplitude can be different, A, I, B, I, C, I, doesn't matter at the moment. And the sum, when you do the average of those ones squared, you will have a value, let's say red, which will be the average of this, which will be something like this, I don't know. So something like this. But you see that it's an oscillation. It's not, before it was a line. If you remember before what I drew before, and I cancel this one here. Now, how to lock the phases? It's not easy. It's technically challenging, and it requires a cavity. Like it's a mess experimentally, but it's been done and can be done. I mean, we have lasers, and we can buy them off the shelf. So it's but the problem is mostly locking the phase. if you want to simply oversimplify the issue. Now, before, what we drew before, it was an intensity which was the mean intensity was a line, and it was not fluctuating like a laser. I mean, sorry. Before it was a line with some fluctuation, because the intensity were different, and then you can get a mass out of it. While now, if you do the average of a sinus square, you will get a straight line. So the intensity is constant in time for the laser, which means it's coherent. Now, this is just for the intensity, but how about the direction? So the direction is a bit more complicated to understand, and I'm not sure if I can grasp the basic idea. But also, if you think about the phase stability, can be in time and in space as well, because a wave that propagates in time and space, so the amplitude will change in time, but also, as I said, in space. So if you think about a sinus of t, we will have a spatial also amplitude, x and y. This is x and this is y. We have a direction. Time is a picture each time. This is a t star, a picture in time, and our light will have a distribution of intensity in some direction. And of course, if these distribution are different as well, so they do not have the same phase associated to it, they will add up randomly, and then will not give a precise direction. It will be basically the light will be expanding as a sphere. Okay, so I mean, there is more to it, but if you want to channel, and this can be this can be coherent in time, but maybe not so coherent in space. And anyway, the emission is not directional, so there is also directionality which plays a role. How all those things are interconnected to each other is a bit more, it's complicated. There is lots of math and physics going on. We need to I mean, essentially you need to solve the equation and see which part is coherent, which is not, which have the same phase relation, which doesn't, and it's not super easy. But the idea is that the basic idea is that if you want to, the coherence is due to the phase relation, to a phase of these waves, of the waves. The other thing is that if you manage to adjust the coherence in space, you can basically select a point and then let the light spread in a more controlled way, which means that essentially you can direct the light very far away by adjusting the initial condition. And this is basically what happens with a laser light, in contrast to a light emitting diode, or in contrast to just a bulb. Okay, so you have a point, a source, which will be coherent in space and time. So x, y, and t will have a nice phase relationships, and this will allow you to direct your beam of light in a particular direction rather than in any direction randomly and homogeneously like in a sphere. Okay, so I hope this is a short video. I hope that I I gave you an idea of why we have laser light that is so directional and powerful with respect to light emitting diode or bulbs light like our normal lamp. And my understanding is that is the coherence and not coherence of the waves is the crucial essential point, and the coherence and non-coherence is due to the phase of all of these sinusoid that are emitted by your source at any time. And also we need to remember there is a space. It's not only time, because a wave is in space and time. So yes, so xy will have their phase as well. So coherence is in spatial domain and in time domain, as it should be. And therefore the thing is quite complicated and involves as I said, different type of equation from lasers, light emitting diode, or just an incandescent bulb. But I think of course I oversimplified the problem and the question, but I hope that the answer is somehow clear. I will so for today I will conclude the video. Next time I will go a bit more in the hydrogen atoms as I did last time. Maybe I will show different orbitals if I can. And for today I will just end with a nice, I think, a nice animation of the difference of the emission of light. One is coherent and one is not coherent. There is one is not completely coherent and one is coherent. Okay, I hope it makes sense, and see you next time. Bye.